Hi, in this video, I'm going to go over the analysis of the boost converter, which is a switch mode power converter that operates by periodically closing and opening this switch here. Now, unlike the buck converter, in which the output voltage is smaller than the input voltage, for the boost converter, actually the boost converter gets its name because the output voltage VO is larger than the input voltage VS. So to analyze this circuit, we're going to assume the following. First is that this circuit is operating in periodic steady state. And this means that we're assuming that the circuit has finished its startup and things have reached an equilibrium. So what this implies is that for the inductor current at the beginning of a period, the inductor current is equal to the inductor current at the end of that period. So this is equivalent to saying that the average voltage of the inductor over a period is equal to 0. And this principle is also called inductor volt-second balance. By the same token, for the capacitor, the voltage across the capacitor at the beginning of a period is equal to the voltage across the capacitor at the end of that period. And that is equivalent to the statement that the average capacitor current over a period is equal to 0. And this statement is known as capacitor charge balance because there's no net there's no net change in the capacitor charge over a period. So the next assumption is the way that we are operating the switch. And we're operating with a certain switching frequency, um, F switching frequency, which means that we have a certain period in which we periodically open and close the switch. Now, the switch is going to be closed for the time interval dt, and for the time interval d prime t, which is equal to 1 minus dt, the switch is going to be open. Now, the third assumption we're going to make is that the inductor current IL of t is going to be continuous, which is equivalent to saying that the inductor current is always positive. So IL of t is greater than 0 for all t. So this is called the continuous current mode. Continuous current mode. So in this first basic analysis, we're going to assume this continuous current mode, but in the next analysis, I'm going to do it for the discontinuous current mode. Now, the fourth assumption we're going to make for this analysis is that the capacitor here is very large, and thus the output voltage VO is purely DC with a value of VO. Now, we will relax this assumption later on when we want to study the output voltage ripple, in which we're going to get some small ripple on top of that DC value. But for now, we're going to make this so-called small ripple approximation for the capacitor voltage, in which the output voltage VO of t is just equal to a constant DC value, VO. Okay, the last assumption for this analysis is that we are using ideal components, so we don't have any parasitic losses or conduction losses from the switches. And this is equivalent to having that 100% efficiency because we're not losing power in any unideal resistive components. So all of the input power gets delivered to that output load resistor in this basic analysis. So we're going to start to analyze this circuit now. And to do so, we're going to draw the circuit for the dt interval and the d prime t interval, and we're going to examine the inductor voltage. The goal is we want to find the average inductor voltage and set that equal to 0, and then we can solve for the conversion ratio. So let's start by examining the circuit for the dt interval in which the switch is closed. So in this first state of the circuit, we're going to have the source voltage here, the inductor, and the switch is going to be closed. Now, under this condition, we will have the diode reverse biased, and then we have the output capacitor and the load resistor R. So in this dt interval, the voltage of the inductor is equal to Vs. And this is because this node is Vs and this node is tied to ground. Now, in this interval where you have the inductor voltage, inductor current circulating in this direction. And this is because the voltage is across the inductor is positive, so we have the inductor current increasing in this direction. Now let's study the circuit for the d prime t interval in which the switch is opened. Now in this state, we have the source voltage here, the inductor, but in this case, the switch is opened. Now because we had the inductor current flowing like so, we can't have the inductor current abruptly change, so it's going to need a path to flow. In that case, the diode is going to become forward biased, turning on and becoming a short circuit, providing a path for the inductor current to flow. So in this case, the inductor current is going to flow in this direction where the diode has made the path available for it. So in this state, the inductor voltage is equal to this node is Vs, and this node, because the diode is shorted, is equal to Vo. So therefore, the inductor voltage is Vs minus Vo. And because we're operating in periodic steady state, we can apply the principle of inductor volt-second balance, which states that the average inductor voltage across a period is equal to 0. So this can also be expressed as during the dt interval, we have the inductor voltage as Vs, and during the d prime t interval, we have the inductor voltage as Vs minus Vo. So this expression equals 0. So we can simplify this expression and isolate things so we can find the conversion ratio Vo over Vs. So with this equation, we can see that we have d times Vs plus d prime times Vs. Now d plus d prime is just equal to 1. So we have 1 times Vs, or just Vs. And then we have another term, which is d prime times negative Vo. So then we have a minus d prime Vo here. So this equals to 0. And if we move this term over, we get d prime Vo equals Vs. And therefore, we find the conversion ratio of the output voltage over the source voltage is equal to 1 over d prime, or 1 over 1 minus d. So we have thus found the conversion ratio of the boost converter. And we know that the duty cycle D is defined as the fraction of the period in which the switch is on. So D we know is always between 0 and 1. So therefore we have a denominator that's always between 0 and 1. And therefore this conversion ratio is always greater or equal to 1. Now VO equals VS when the duty cycle equals 0. And we can see that makes sense because when the duty cycle is 0, the circuit is just constantly in this state because the switch is always off in duty cycle equals 0. In that case, this circuit under equilibrium, the inductor just becomes a short circuit, and we have the source voltage simply tied to the output voltage. In that case, Vs equals Vo. Now, when we operate the circuit with the duty cycle greater than 0, we'll see that the output voltage is greater than the source voltage. Now we want to draw out what the inductor waveforms look like. So for the inductor voltage VL, let's draw that out first. So here we have the time axis, and the vertical axis is VL. And then for the tick marks, we have the dt interval, and then next we have the period t. And during the dt interval, we found that the inductor voltage is positive with value Vs. And then for the d prime t interval, we had discovered that the inductor voltage is negative because it's Vs minus Vo, and Vo is greater than Vs. So in this case, because we're operating in periodic steady state, the waveform simply repeats continuously afterward. And we can see from the inductor volt-second balance principle, as we had stated before, the average inductor voltage over a period equals 0. So what that means is that this positive area above the time axis balances out with the negative area under the time axis, resulting in an average inductor voltage over a period of 0. So this is our inductor voltage waveform. Next, we want to find what the inductor current waveform looks like. So to do that, first we recall the assumption that we're operating in continuous current mode, which is IL of t is greater than 0 for all t. So that simply means that the inductor current never reaches 0. Now later on, we will analyze the case for discontinuous mode as well. So in this case, what is the slope of the inductor current during the dt interval? So we had found here during the dt interval that the inductor voltage is a constant Vs. So in this case, the inductor characteristic equation is VL equals L dIL dt, and this equals a constant value of Vs. So in this interval, the inductor current IL is increasing linearly because we have a constant voltage across it. So we can write this as Vs over L is equal to dIL dt. And because it's increasing linearly, we can just call this change delta IL. And the time duration is the dt interval. Likewise, for the d prime t interval, we have the inductor voltage as Vs minus Vo, and then divided by L is equal to the change in the inductor current over the d prime t interval, which is our time duration. So these are our inductor current slopes. We have found that this is the slope. So we in our waveform, we can draw that out. And note that this value here is negative. And it's negative because V out is greater than Vs, as we have also demonstrated here in this waveform. While here, note that it's positive. So the inductor current essentially is increasing in this interval, and it is decreasing in this interval. So what the waveform is going to look like is in the dt interval, we will have the inductor current increasing with slope Vs over L. And then in the d prime t interval, it will be decreasing with the slope Vs minus Vo over L. And because of the periodic steady state operation, this waveform will repeat continuously. So these are our waveforms for the inductor voltage and current. Now, what about the waveform for the current through the diode? So if we look back on this circuit, in the dt interval, this is the current through the diode, which is equal to 0. Now in the d prime t interval, the current through the diode is equal to the current through the inductor. So we've also figured out the waveform for the diode. So in the dt interval, it's equal to 0. And then in the d prime t interval, it simply equals IL. So this is our diode current waveform. It simply follows IL in the d prime t interval, and it's 0 otherwise. What about the capacitor current? So if we note the capacitor current in the dt interval, let's call IC this direction, and then this is IR. Now, because of the small ripple approximation, IR is just equal to V naught over R. So we can see that in the dt interval, the capacitor current IC equals negative IR by KCL. So it equals negative V naught over R in the dt interval. What about the d prime t interval? In the d prime t interval, we have this as IC, and then IR. IR is still equal to V naught over R, just by a simple Ohm's law for the resistor. And in this case, we have that the capacitor current by KCL is equal to IL minus IR, which is V naught over R. So therefore, we have the capacitor current in the d prime t interval is equal to the inductor current, but then it's shifted down by this DC value of V naught over R. So therefore, for our capacitor current waveform, we can also draw that out. And note, from our capacitor charge balance equation, remember that we had the average capacitor current over a period is equal to 0. So in the dt interval, we had the capacitor current is equal to negative V naught over R. So we had this is equal to negative V naught over R. And then in the d prime t interval, we have it equal to the inductor voltage, but shifted down by V naught over R. So it takes on the same shape as IL, but we have the output load current subtracted from it. And likewise, we'll see this pattern repeat continuously because we're operating in periodic steady state. So because of this principle here of the capacitor charge balance, we will have the average capacitor current equal to 0. So that means that this negative area here will balance with this positive area here. And this is equal to IL in this period minus V naught over R. So we've found some of the key voltage and current waveforms in our circuit. And the next step is we want to quantify what the average inductor current is. So what is this average inductor current here? So we can go ahead and find the average inductor current IL here by using the fact that our assumption we had the input power is equal to the output power. So if we know in this circuit, the input power is equal to the source voltage times the current that the source voltage is delivering to the rest of the circuit. Now, this current is just equal to the inductor current. So we have the input power is equal to the source voltage times the DC inductor current. So therefore, we have VSIL is equal to the output power, and the output power we know is equal to V naught squared over the load resistor R. And it can also be expressed as the output voltage times the output load current IO. Now, we can substitute our voltage conversion ratio in for V naught. So we know that V naught is equal to Vs over 1 minus D. So therefore, if we substitute this expression in for V naught here, we get that VSIL is equal to Vs divided by 1 minus D squared over R. Now this is equal to Vs squared over 1 minus D squared on the bottom times R. So therefore, we're looking for the average DC inductor current IL. So we can divide both sides by Vs, and we get that the average inductor current is equal to Vs divided by 1 minus D squared times R. Now we can also express the output voltage like before as V naught I naught. So we can also just divide both sides by Vs here to get IL. So this also equals V naught I naught over the source voltage. And likewise, we have the output power as V naught squared over R as another expression for P out. So we can also express the same thing as V naught squared over R times Vs. So these are three equivalent ways to express the average DC inductor current. Now, what about the maximum inductor current and the minimum inductor current? So we found the DC inductor current. What about this maximum point here, I max, and this minimum inductor here, I min? Now, we want to find because we know the DC component, what this delta IL is. Now, delta IL, we know because we know the slope during the dt interval is Vs over L, we can just multiply the slope by the time interval of dt, and that's going to give us this change, delta IL. So therefore, if we want to find I max is just equal to the DC current plus delta IL over 2, while I min is equal to the DC current minus delta IL over 2. And you can just see that very plainly because this is delta IL over 2 and this is delta IL over 2. So we know this DC component, so we can just add and subtract the delta ILs to get our min and max. So these two expressions, we can plug in the expressions for IL and the expressions for delta IL, and we can get an expression um, with our various parameters for Imax and Imin. So in this case, we have, let's write that here. We have, let's use another color. Imax is equal to IL plus delta IL over 2. And let's use this expression here. So we have the DC component as 1 minus Vs over 1 minus d squared R. And then the delta IL is Vs dt over L. And then we need the factor of 2. Now, likewise for I min, we had found that as IL minus delta IL over 2. And that equals Vs 1 minus d squared R minus Vs dt over 2L. Now, in our assumptions, it was key that the inductor current is continuous, meaning that I of t is always positive. And that means that we need that the minimum inductor current to be always greater than 0. So in this case, if we require that I min is greater than 0, we can solve for this inequality here to find the inductance and the period that we would need to ensure that we have continuous operation. So in this case, we have Vs over 1 minus d squared R is greater than Vs dt over 2L. And we just move this term to the other side. Now, this period t, we can also express as 1 over the switching frequency, so 1 over f. So this equals Vs d 2LF. Now, we can see that in this inequality, we have the VS's on both sides. So we can cancel that out, and we can move L and F, which are parameters that we can control in our design of the boost converter, to the other side. So then we have LF is greater than D times 1 minus D squared R over 2. So this is a key design equation. Now, if we select the switching frequency F in our design already, and now we just want to choose the inductor, we can divide both sides by F, and we get that the minimum inductance is D times 1 minus D squared R over 2F. Now, this equation is key because it ensures we operate in continuous current mode. Now, for our analysis so far, we have assumed that the output voltage is a completely constant DC value, VO. However, if we want to go a step further and examine the output voltage ripple, we can no longer assume the small ripple approximation. So to examine what the output voltage ripple is, we'll look at the capacitor charge. So we know that for a capacitor, Q equals CV. Now, this also means that the change in the charge stored in a capacitor is equal to the capacitance times the change in the voltage across the capacitor. In this case, the capacitor's voltage is the output voltage because we have, as our circuit is configured, we have the diode here and then the capacitor and the output load resistor. So in this case, we have VO here and the load resistor and the capacitor. So this means that the output peak-to-peak voltage ripple is equal to the change in the charge stored in the capacitor over the capacitance C. So in this case, we want to find what the change in charge is for the capacitor. So in this case, we can examine the capacitor current waveform that we have drawn. And in this case, we can look at the dt interval and figure out during this interval what the change in capacitor charge is. So we know the current is negative V naught over R. So the capacitor current times the time interval dt will give us the change in capacitor charge. So now that we found delta Q as this expression, in fact, we can just take the magnitude of it as that is what we're looking for. So we can substitute that expression in and we can put absolute value signs because we're only looking for the magnitude. And that equals V naught over R dt is our delta Q, and then times 1 over C. Now, this T, as before, we can express that as 1 over F. So our expression for delta V naught is equal to VO d FRC. And we typically express the output voltage ripple as delta V naught over V naught. So this is the ripple ratio. So if we divide both sides by V naught, we get delta V naught over V naught equals D over RCF. So this is a key expression. And if we want, we can express the capacitance that we're looking for. We can just isolate C in this equation and divide both sides by the ripple ratio, and we get C equals D RF times delta V naught over V naught. So this allows us during the design process, if we have a certain ripple ratio we're looking for, maybe like 1% ripple ratio, then it can help us determine what capacitance value we need to choose. Now, it is important to keep in mind that in the real circuits, the capacitance will have an equivalent series resistance that's unavoidable. And this resistance is RC, and this whole branch is parallel to the load resistor R. So in this case, actually, This ESR resistance, this little RC, will also contribute, sometimes very significantly, to the output voltage ripple. So in that case, we need to consider delta VO due to the ESR of the capacitor as the capacitor current, be the change in capacitor current times the ESR resistance. So this will be an additional factor to consider when you're looking at the output voltage ripple. In our basic analysis so far, we have assumed that components are ideal, and we get that the input power is equal to the output power, and we thus get 100% efficiency. In this case, from our analysis, we had found that the voltage conversion ratio, which is the output voltage over the source voltage, is equal to 1 over 1 minus d. Now, what happens if the duty cycle approaches 1? Then the conversion ratio approaches infinite. So that means that theoretically, we have some DC-DC converter that has a conversion ratio that goes to infinity. But actually, in practice, this doesn't work. And this is because of a significant contributing factor being the series resistance of an inductor. Let's call it RL. So how does introducing a series resistance of the inductor affect our conversion ratio? So we can now study the circuit by assuming that this RL introduces a resistive power loss in the circuit. Now, in our analysis, we're going to assume that the inductor current is approximately constant. This is just to ease our analysis a bit. So in this case, we have the input power, the power that the source is delivering to the circuit, PS, is equal to the output power. However, we also have some power loss in the resistor, so that equals the power loss due to the series resistance. Now, in our boost converter, there is something to notice here, and that is that the source current, let's call it IS, IS is equal to IL. This is just because the inductor is in series with the source voltage. Also, at the output current IO is equal to the DC diode current. And this is because there's no DC current through the capacitor because of capacitor charge balance. So therefore, with this in mind, we can write the expressions for the input power and the output power. So the source power is equal to Vs times Is, but we know Is is just equal to IL. And then the output power, PO, is equal to the output voltage times the output current. And we know the output current is just equal to the DC diode current, ID. What about the power consumed by the series resistance RL? Well, we have an I squared R loss, so that's just equal to IL squared times RL. Now, in the D prime interval, we have the diode current being equal to the inductor current, while in the regular DT interval, the diode current is equal to 0. So therefore, we know that the diode current ID is equal to IL times 1 minus D. So if we substitute that in, we get VSIL is equal to VO IL times 1 minus D plus IL squared times RL. Now, all of these terms have an IL in them, so we can divide that on both sides. So we get VS equals VO times 1 minus D plus IL RL. Now, we can also now express the average inductor current, which we assume is just the constant current through the inductor, is equal to ID over 1 minus D. That's just dividing 1 minus D on both sides of this equation. And we get that this equals V out over R, because we know the diode current is equal to the output current. And we can substitute this expression in for our IL here. So this equals V out times 1 minus D plus V out over R times 1 minus D times RL. So this equation, Vs equals this. We can then solve for V out over Vs. And if we do so, just manipulating some of this algebra, we get VO over Vs equals 1 over 1 minus D times 1 over 1 plus RL divided by R times 1 minus D squared. So this is our voltage conversion ratio if we considered the series resistance of the inductor. Now what we see is that this conversion ratio is the same as that for an ideal converter, which is 1 over 1 minus D. However, we also get this multiplicative factor, which accounts for the inductor's resistance. Now, if the inductor's resistance is equal to 0, then the denominator just becomes 1, and this factor is just equal to 1. So what it turns out is that the conversion ratio will look something like this. So for the ideal boost converter, if we draw the duty cycle axis, let's call this the duty cycle axis, where this is 1 and this is 0. In the ideal case for duty cycle equals 0, the conversion ratio, V out over Vs, is just equal to 1. And then as the duty cycle increases and gets to 1, we get that the conversion ratio approaches infinite. Now, this is the ideal converter case. Now, if we include the inductor resistance RL, then actually the voltage conversion ratio to the duty cycle curve will look something more like this. So at lower duty cycles, we'll get the curves are about equal. However, as the duty cycle increases, the conversion ratio won't approach infinite. It'll actually fall back down like this. And actually at duty cycle is 1, actually it might drop to 0. So this is the non-ideal case where RL is not equal to 0. So in the ideal case, we had the inductor series resistance equals 0. And in this analysis, we had also assumed other components are ideal. Actually, we will see that other parasitics in the circuit will also contribute to a less than ideal conversion ratio. And because of this loss in the series resistance, In the efficiency curve versus duty cycle, for the ideal case, we had 100% efficiency across the duty cycles. So this is uh, efficiency, and we had 100% for ideal converter. However, with a non-zero inductor resistance, we'll see that the efficiency drops as we increase the duty cycle. So it will look something like this. And this is 0% efficient. So this is the analysis for a buck converter where we consider the inductor's resistance. So we've analyzed the circuit so far in the continuous current mode. Now we're going to move on to analyzing the boost converter in the discontinuous current mode. In the discontinuous current mode for the boost converter is actually used in some applications for control reasons. So it's actually very good to study. So let's start by looking at the inductor current waveform in the discontinuous mode. So by definition, the discontinuous current mode, we're going to have the inductor current reach zero. So the inductor current IL, it's going to start at zero current. It's going to rise up to some maximum current I max. And this point occurs at time dt. Then for the next interval of time, d1t, the inductor current's going to fall back down to zero, and then it's going to remain at zero for the remainder of the period t. And this cycle will just repeat. Because we are in periodic steady state. So what does the voltage across the inductor look like? Well, this is very similar to our continuous current mode operation analysis, except that we have this period where the current is equal to zero. So in the dt interval, we have that the inductor voltage is equal to the source voltage Vs. And then in the d1t interval, we have that the source voltage is equal to the source voltage minus the output voltage. And then for the rest of the period, we have that the inductor voltage equals zero. This just repeats periodically and so on. So this is the inductor voltage waveform. Now, what does the diode current waveform look like? So we know in the dt interval, the diode current is equal to zero because the diode's reverse biased. So in the dt interval, the diode current ID is equal to zero. Now in the d1t interval, we have that the diode current is just equal to the inductor current. So in this case, it's just going to follow the inductor waveform. It's going to reach some maximum current I max, which is the same as that of the inductor current. And then it's going to be equal to zero because it's off in the period, in the interval until the end of the period. So this is what the inductor, what the diode current waveform looks like. So in discontinuous current mode, remember that we're still in periodic steady state. So inductor volt-second balance still holds, and capacitor charge balance still holds. This is just because we need the current through the inductor to be the same at the beginning and end of the cycle, which is just 0, and the capacitor voltage to be the same at the beginning and end of the cycle. So this means that if we study the average voltage, VL, of the inductor over a period, it must be equal to 0. So this equals if we look at this waveform, the dt interval, we have d times Vs, and in the in the d1 interval, we have Vs minus Vo. So this expression equals 0. So we can solve for the ratio of Vs to Vo by moving these terms around. And if we do so, we find that the voltage conversion ratio, Vo over Vs, is equal to d plus d1 over d1. So if we want to solve for the voltage conversion ratio, we need to find some way to find an expression for d1. So we can do that by looking at the average diode current. So the average diode current in this case, we see that ID, if we just take the area under this curve and then divide it by 1 over the period times the area of the curve, that equals, so the base is d1 times t, and then the height is I max. And for the area of the triangle, we need to multiply by half. Half times base times height. So the t's will cancel out, and we're going to get that the average diode current is equal to half times d1 times I max. Now note that the maximum current I max is just equal to delta IL, which we've seen many times before. And in the dt interval, we have that this slope equals Vs over L. So therefore, delta IL, which equals I max, is just equal to Vs over L times the duration of the interval, which is dt. So we can plug this in for I max here, and we get half times d1 times Vs dt over L. Now there's one more thing to note. In this boost converter, we have that the average diode current is equal to the average load current, which is equal to V naught over R. This is because the average capacitor current equals 0, so this current must be equal to this current. Therefore, we can equate this average diode current to be equal to the average load current, which equals V naught over R. So with this equation, we can solve for D1. So using this equation, we will find that D1 is equal to V naught over Vs times 2L over R dt. So now we can express, using this expression for D1, we can plug this into our voltage conversion ratio equation, and we'll find that we're going to get a quadratic equation, V naught over Vs V naught over Vs squared minus V naught over Vs minus d squared RT over 2L is equal to 0. Now, if we solve for this quadratic equation for the voltage conversion ratio VO over Vs, we'll find that VO over Vs is equal to half times 1 plus square root of 1 plus 2d squared RT over L. So this is our voltage conversion ratio for the boost converter in DCM. So in discontinuous current mode. Now, the discontinuous current mode happens when the D1 is equal to 1 minus D. So we can see here, if this interval is equal to this interval, then we're on the boundary between discontinuous and continuous conduction mode. So this is one condition. And the other condition we had found previously during our continuous current mode analysis, and that's where I min, the minimum inductor current, is equal to 0. So these two conditions establish the boundary between continuous and discontinuous operation. And the boost converter can, for the same topology and the same values of our circuit components, the circuit can operate in the continuous or discontinuous mode depending on the duty ratio. And for a given output voltage, we can vary the duty ratio accordingly to get that value. So overall, this is the analysis for the boost converter, both in the continuous conduction mode as well as the discontinuous conduction mode. And I hope you found this video helpful in studying switch mode power converters. And if you'd like to watch more content like this in the future, please give this video a thumbs up and subscribe to my channel. I hope you have a good day and hope to see you in future videos. Thank you very much.